Today's notes are going to be over alternating series. So, how do you know a series is alternating? Well, that's going to be if the terms of the series switch between positive and negative and positive and negative and positive and negative. And there's a number of different ways that that can happen. We will look at several in our example problems today. But before we get started, we're going to kind of make up a little flow chart that will help us to determine whether an alternating series is absolutely convergent, conditionally convergent, or divergent. So let's start with a series from n equals 1 to infinity, and the series rule will be represented by a sub n. And we're posing this question: is the series absolutely convergent conditionally convergent or divergent? So you might notice that we have three choices this time, where in the past we've just said, is it converging or diverging? Here we've got two different types of converging alternating series: absolutely convergent and conditionally convergent. And we want to be able to differentiate between the two. So we're asking ourselves this question, and that takes us to step 1, which is to do the test for absolute convergence. So this is what we check first, and the order matters. Often we will use the ratio test. However, other tests can work as well. And so the way we're going to do that is we're going to take this series and put our series rule in absolute value bars. So we're basically going to pretend like it is not an alternating series, and then test to see if that series converges or diverges by whatever means seems most appropriate for the given series. If the answer to that is that yes, the absolute value of a sub n converges, then a sub n without the absolute value bars converges, and we call that absolute convergence. However, if the answer is no, then we have to go to step 2, and that is the absolute value of a sub n does not converge, so we're going to use the alternating series test. Okay, and so for the alternating series test, it's a two-step process. First, we're going to check to see if the absolute value of the terms decrease. And I didn't write that out in a sentence. I just put the word terms in absolute value bars. How do you like that? The absolute value of the terms decrease. So like as I move along in my series, the value of each fraction or whatever is getting smaller. Basically, like the numerator's growing would be a common way to see that. Secondly, the limit as n approaches infinity of the absolute value of a sub n has to be going to 0. So if the terms are decreasing and heading towards 0, then if the answer to both of those is yes, then we say that the series is conditionally convergent, which means that it requires the condition of alternating in order to be a converging series. If this series was not an alternating series, it would be diverging. If the answer to this is no, and it could be either one of these is no, it doesn't have to be both, then we're going to say that the series is divergent. Okay, so this flowchart is something you're going to want to memorize and feel pretty confident with as you move into upcoming assessment. So let's do some example problems that involve alternating series. So to start, we're going to look at the sum from n equals 0 to infinity of negative 10 to the nth power over n factorial. Okay, so we can tell this is an alternating series because we have a negative raised to a power. So any even power will cause the output to be a positive term, and every odd power will cause the output to be an negative term. So it is alternating. So we want to start with step 1, the test for absolute convergence. How does that work? Well, we're going to say the sum from n equals 0 to infinity of the absolute value of negative 10 to the n over n factorial. And what does that mean? Well, this is the same thing as the sum from n equals 0 to infinity of 10 to the n over n factorial, because that negative being raised to the nth power is not going to impact the series anymore since we've got the absolute value bars. So looking at this series, I think I'm going to use the ratio test to determine if this is a converging or diverging series. So we're going to look at the limit as n approaches infinity of 10 to the n plus 1 over n plus 1 factorial times, divided by the original, but I'm going to multiply by the reciprocal, n factorial over 10 to the n. Okay, so we're going to work on that. The limit as n approaches infinity of, that would be 10 to the n times 10 to the first times n factorial over n plus 1 times n factorial times 10 to the n. And so we have some common factors in our numerator and denominator that will divide out. N factorial over n factorial divides out. 10 to the n over 10 to the n divides out. So I've got the limit as n approaches infinity of 10 over n plus 1. That's all that's remaining. So as I send this n in the denominator to infinity, this fraction is just like a constant over infinity, which is approaching 0. So this limit is equal to 0. 0 is a number less than 1. So we say that this is absolutely convergent. Okay. It's absolutely convergent. We use the ratio test to determine that. So, number 2. We're going to do the sum from n equals 1 to infinity of -1 raised to the power of n plus 1 divided by the 4th root of n. So, first thing we're going to do is check for absolute convergence by looking at the absolute value of this series. So if I put it in absolute value bars, -1 to the n plus 1 power is just going to be 1 on top always, because it's not going to alternate back and forth between -1 and +1 anymore. So I'm going to say this is equal to the sum from n equals 1 to infinity of 1 over. Now the 4th root I want you to consider is the same thing as the 1/4 power. And so what do we know about this series? Is this series converging or diverging? What type of series is this? I don't need to use the ratio test on this thing. It's just a p series, which is probably like the easiest convergence test we have. And since p is less than or equal to 1, we say that this is diverging. Now, if it is not converging, that does not mean that this original series with the alternating signs is diverging. This just means that we proceed to step 2 and check to see whether it is conditionally convergent or divergent by using the alternating series test. So this does not mean that the original series is diverging. It's this absolute value series that is diverging. So we're going to check for conditional convergence. That's what we're going to check for next. So how do I check for this? Well, I need to check to make sure that the absolute value of the terms is decreasing. Okay, so the absolute value is this series right here. 1 over the 4th root of 1 plus 1 over the 4th root of 2 plus 1 over the 4th root of 3 plus 1 over the 4th root of 4 plus ... What do you notice about these? Well, as I take the 4th root of a bigger and bigger number, the 4th root is larger and larger. The denominator is growing while the numerator remains constant. So the absolute value of the terms decrease. So the first item that we need to examine for the alternating series test did become true. So next, the next thing we have to look at is the limit of the absolute value. I'm running out of space here. I don't want to, I'm going to squeeze it. See if I can zoom in a little here. The limit as n approaches infinity of the absolute value series, which is 1 over the 4th root of n. So as n goes to infinity, the denominator grows, the numerator remains constant. That does approach 0. So since the limit of the absolute value series is 0 and the absolute value of the terms decrease, those two things mean that yes, the series is conditionally convergent by the alternating series test. I apologize for my crazy little writing up the page here, but I just wanted that problem to fit and it didn't quite do that. Okay, so we've seen one which was absolutely convergent and one which had conditional convergence. Excellent. Let's try another problem. Number 3, we're going to look at the sum from n equals 1 to infinity of -1 to the nth power times n over n plus 5. Okay, so the first thing that we need to do is check to see if it's absolutely convergent. or check for absolute convergence. How do we do that? Well, we're going to look at this series where our series rule here is in absolute value bars. Now, how is that going to change? Well, the -1 to the nth power will no longer cause the series to flip back and forth between positive and negative because it's always going to be positive. So that could just come out, and it's just going to be n over n plus 5. Now, what do we know about this series? Well, probably more than one way to approach the convergence test for this, but I'm going to say that I notice that the limit as n approaches infinity of n over n plus 5 is equal to 1, which is not equal to 0. So it is divergent by the divergence test. Because if you will recall, every limit must equal 0 in order to be a possibly converging series. Anything that does not, where the limit as n approaches infinity does not equal 0, is diverging by the divergence test. Now, that does not mean this original series is necessarily diverging. The next thing we have to do is check for conditional convergence. So that's a two-step process. First, we need to check to see if the absolute value of the terms decreases. So if I put in 1s, because I'm starting my series at n equals 1, 1 over 1 plus 5 is 1/6. And then if I put in 2s, 2 over 2 plus 5 is 7. And then if I put in 3s, 3 over 3 plus 5 is 8. And then if I put in 4s, 4 over 4 plus 5 is 9. And then if I put in 5s, 5 over 5 plus 5 is 10. Wait a minute, this is a half. Is a half smaller than a sixth? These fractions are not getting smaller. The absolute values of the terms do not decrease. Therefore, the series diverges by the alternating series test. We don't even need to check the limit because the first condition for conditional convergence fails. So it is a diverging alternating series. Okay, number 4. I would like you to try this one on your own and pause your video and then come back to see how you did. The sum from n equals 1 to infinity of -1 to the n, 16 to the n, over 5 to the n. Okay, so pause your video and see if you can determine whether this alternating series is absolutely convergent, conditionally convergent, or divergent. Okay, I'm going to assume that you paused your video and you gave this problem a try. Did you get that the series is diverging? Hopefully you did. If you put it in absolute value bars, you get 16 to the n over 5 to the n as your series rule. And that could be written as 16 over 5, the quantity 16 over 5 to the nth power, which is a geometric series, and the r value is greater than 1. So that means that the series is diverging. The absolute value of the series is diverging, so it does not have absolute convergence. And if you check for conditional convergence, the numerator is outgrowing the denominator, so it is the absolute value of the terms do not decrease, so it diverges by the alternating series test. All right, hopefully you got that one right. Now, number 5. The sum from n equals 1 to infinity of the sine of pi over 2 plus n pi over n to the 7/2 power. Now, you might be saying to yourself, Mrs. Heiss, is that even an alternating series? It doesn't quite look like it. I don't see a negative raised to an n power. Well, it is a unique alternating series, but this is another way that we can make a series switch back and forth between positive and negative. Let me explain. Let's say that n is equal to 1. Then I've got the sine of pi over 2 plus 1 pi, which would be like 2 pi over 2. So this is sine of 3 pi over 2. Okay, so where is 3 pi over 2 on your unit circle? That is directly down from the origin, and since the sine is your y coordinate, it is -1 for your sine of 3 pi over 2. Now what if I have n equals 2? Well, then I'm going to add 2 pi to pi over 2. So 2 pi to pi over 2 is the same thing as like 4 pi over 2 plus pi over 2, which is the sine of 5 pi over 2. And where is 5 pi over 2 located on your unit circle? Well, since you've added 2 pi, you've basically gone a whole circle from pi over 2, which is directly up from the origin. So this is a y value of 1 on the unit circle. Now what if n is equal to 3? We're going to have the sine of 7 pi over 2, which is the same thing as 3 pi over 2, which is -1. And if you have n equals 4, you're going to have the sine of 9 pi over 2, which is the same thing as pi over 2, which is +1. So you're alternating back and forth between basically pi over 2 and 3 pi over 2, pi over 2, 3 pi over 2, back and forth. So it's, -1 and 1, -1 and 1. And so that's how the sign is alternating. So watch for this, because this is a way that we can cause a series to be an alternating series without just putting a negative raised to a power. So if I want to check this one for absolute convergence, that means I'm going to look at the sum from n equals 1 to infinity of the absolute value of the sine of pi over 2 plus n pi over n to the 7/2 power. And what is that going to look like? Well, that is basically going to take my numerator, which was going -1, 1, -1, 1, and just make it always a +1 on top over n to the 7/2. Now, what do you know about this series? This is a p series, and the p value is greater than 1, which means that this series is, therefore, it is absolutely convergent. Okay, the absolute value series is a p series, and the p value is greater than 1, so this is an absolutely convergent series. Okay, next let's look at number 6. Yeah, I think I've got room for it here. All right, so we're going to do the sum from n equals 1 to infinity of -1 to the n plus 1 power over n plus 2. So first thing we want to do is check to see if it's absolutely convergent. So I'm going to throw it in an absolute value bar. And what is that going to do? Well, the numerator is no longer going to switch back and forth between positive and negative. It's just going to be 1 over n plus 2. Now, I want you to notice that this series is a comparison series to the harmonic series. Oops, I forgot the little summation from n equals 1 to infinity of 1 over n. Now we know that the harmonic series diverges. So we're going to need to use a comparison test to see if this series converges or diverges. So we're going to do the limit as n approaches infinity of 1 over n plus 2. I'm taking my original series and I'm going to multiply it by the reciprocal of my comparison series, which is going to be the limit as n approaches infinity of n over n plus 2. So that limit is going to approach 1. So the limit is positive and finite. Therefore, both series do the same thing. And we said that this one was diverging because it's harmonic. So both series diverge. Okay. And that's by the limit comparison test. So remember, this was our test for absolute convergence. So it is not absolutely convergent, but it still could be conditionally convergent. So let's check for conditional convergence next. So the first step is to take our absolute value series and look at the absolute value of the terms. So if I sub in a 1, my first, and I'm looking at this one right here, 1 over n plus 2, my first term would be 1/3, and then the next one would be 1/4, and then 1/5, and then 1/6. So you can see that the absolute value of the terms decreases. Okay, now step 2, we need to check the limit as n approaches infinity of the absolute value series, 1 over n plus 2. So if I send this n to infinity, as n goes to infinity, it gets larger and larger and larger and larger. The value of the denominator increases and increases and increases, and as the value of the denominator increases with only the constant on top, the overall fraction is approaching 0. So both of the conditions for conditional convergence have been met. The absolute value of the terms decreases. The limit as n approaches infinity of the absolute value series is equal to 0. So we can say that the series is conditionally convergent by the alternating series test. Okay. And definitely cite that test name in your work, because you are justifying your answers. We're not just asking yes, no kind of question here. You need to be able to support it. Okay, number 7. And this is our final example. Okay, so this example is a little different. I've got a function equal to the series from n equals 0 to infinity of -1 to the nth power times x to the 2n power over 2n plus 1 factorial. We want to show that 1 minus 1 over 3 factorial approximates f of 1 with error less than 1 over 100. Okay, in order to do this problem, you need to know an important fact. So when I have an alternating series, the value of each term is like going positive, negative, positive, negative, positive, negative, positive, negative, and approaching 0 usually, back and forth around some, x-axis or whatever. So if I were to give an approximation for the sum over time, by just adding up the first few terms. Let's pretend that I start with a positive value. The first value might be positive, and it's much more than the actual sum. Then the next one would be negative, and it's going to take it down less than the actual sum, then more, then less, then more, then less, then more, then less. And the more you go on and zigzag back and forth, the closer you get to the true sum. Okay, so if I approximate the sum by using however many, terms of the series, the amount of error that exists is always going to be less than or equal to the first term that I leave off. So whichever term is the first one that I leave off, the very next term, the error is going to be less than or equal to that term. And that's because the next one is going to come back and be the opposite sign, and it's going to counterbalance a little bit of that, but not all of it, and it's always going to keep getting more and more accurate. But the most error that I could possibly have is the first term that's left off. So they're saying they want us to show that this value right here approximates f of 1. So if I were to use a 1 for my x, with error less than 1 over 100. So exactly how would that work? Well, let's look at let's first spell out this series, the first few terms. So I've got f of x is equal to -1, we're starting with n of 0, x to the 2 times 0 over 2 times 0 plus 1 factorial. There's my first term. The next one will be if n is 1. -1 to the first, x to the 2 times 1 over 2 times 1 plus 1 factorial. And then we're going to have if n is 2. So -1 squared, x to the 2 times 2 over 2 times 2 plus 1 factorial plus ... So f of x will equal, let's see, this is going to be positive, okay? Anything to the 0 power is 1, so the numerator is just positive 1. And then the denominator here is 0 plus 1, which is 1 factorial, so that's just 1. The first term is 1. Now let's look at the next term. The numerator is going to be negative x squared, so let's put minus x squared over 2 plus 1, which is 3 factorial. Okay, then the next term is going to be positive x to the 4th over 4 plus 1 is 5 factorial. Now, I didn't write out the little rule for the next one, but I bet you're starting to see a pattern already. It looks like the terms are alternating, so I'm going to have negative next. Then I'm going to have x to the, this was 2, this is 4, the next one's going to be 6, and then divided by 3, 5, 7 factorial. And then the next term will be positive, and it'll go on and on like that. Okay, so let's talk about if I'm plugging in a 1 for x. That's what we're talking about. We want to approximate f of 1. So the first term is 1. Then I'm going to have minus 1 over 3 factorial plus 1 over 5 factorial minus 1 over 7 factorial plus ... So they're saying show that 1 minus 1 over 3 factorial, which is this part right here, approximates f of 1 with an error less than 1 over 100. Well, if I use this first two terms to approximate f of 1, then I know that the error is less than or equal to the first term left off. So 1 over 5 factorial. So this means my error, sorry, I don't think you could see that I zoomed in. Error is less than or equal to 1 over 5 factorial means 5 times 4 times 3 times 2 times 1. Okay, so what is that? 20 times 3 is 60 times 2, 120 times 1 is 120. So the error is going to be less than or equal to 1 over 120. And they wanted us to show that the error would be less than 1 over 100. Well, if it's less than 1 over 120, that's definitely less than 1 over 100, because 1 over 100 is a bigger number than 1 over 120. Remember, the bigger our denominator is, the smaller the overall value of the fraction. So by doing this work right here, we have just shown that the error has to be less than 1 over 100, because it's actually less than 1 over 120. So the amount of error in a partial sum, which means just adding up a discrete number of terms, a discrete number of terms, in a partial sum of an alternating series is less than or equal to the first, or the absolute value of the first, the absolute value of the first term left out of the partial sum. So just however many terms you go out, look at the very next one that would follow. That term, whatever it is the maximum amount of error that you could possibly have in your partial sum. It will be less than or equal to that term. Okay? All right, that concludes our look at alternating series for today. I hope you learned a lot, maybe had a little fun. It's kind of interesting. Please let me know if you have any questions or you need any help at all. And good luck with your homework. Reach out if you need me. Have a fabulous day, and bye for now.